Today's lesson is an AP lesson, which comes from Math 20-1, where we start to look at angles beyond the 90 degrees. An angle in standard position is when we rotate a ray around the origin of our Cartesian plane in a counterclockwise direction. So here's my Cartesian plane. We know the origin is where the x and y axes meet. We also know quadrant 1 is where both the x and y coordinates are positive, and then rotating counterclockwise we get quadrant 2, quadrant 3, and quadrant 4. At the origin here will be the start of my ray, and then I'm going to draw the one arm like that. If I now take that ray and begin to rotate it counterclockwise, however many degrees I rotate, let's say the second arm ends up there, this now becomes my angle of rotation. To be an angle in standard position, we want to make sure that that vertex lies at the origin. The initial arm of the angle is the one that lies on the positive x-axis. So this is my initial arm. The terminal arm, so think this is where we end up, we're terminating here, that is the final position that we end up in. And again, that angle of rotation is how far we've rotated counterclockwise. 3 angles would be considered angles in standard position. In this one, we don't have the vertex at the origin, so it should be right here. In this one, we don't have the initial arm on the positive x-axis. And similar here, we don't have the initial arm on the positive x-axis. This is on the negative x-axis, so we don't consider any of those angles in standard position. We're going to take a look at how to draw an angle of rotation given the information provided. In the first example, we have to sketch that angle of rotation, and on the terminal arm, we have to pass through that point. So I take my little graph here. We know this is the x-coordinate and this is the y-coordinate. So on my x-axis, I'm going to go to positive 2. On my y-axis, I'm going to go to 1, 2, 3, 4, 5, 6, 7. I just roughly approximated where that would be. I also know that the terminal arm passes through that point. So I can draw, I know that my vertex is on the origin, and my terminal arm is going to go through that point. I also have an initial arm that will lie on the positive x-axis. That initial arm rotated counterclockwise to this point where we're passing through that 2, 7. So my angle of rotation is that angle there. Similar to this first example, I have a few other examples where we terminate in different quadrants. So this one terminates in quadrant 2, where x is negative, y is positive. The next one terminates in quadrant 3, where both x and y are negative. And the final one terminates in quadrant 4, where x is positive, but y is negative. So you can see that this is where we started, and we rotated that ray around to end up in the final position. We can use this point on the terminal arm to define some trigonometric ratios for these angles in standard position. I assumed that x and y were both positive in this case, so I just put a point here. We know the terminal arm is going to pass through that point. I can create a right triangle by drawing a vertical line from this point down to the x-axis, so that's going to form a 90-degree angle. We know that we can use our primary trig ratios, sine, cosine, and tangent, in any right angle triangle. If this is my angle of rotation, in this first example, I know that whatever point that is, this is how many units we moved on the x-axis, so that's going to be that value. And then this is how many units up we went on the y-axis, which is going to be that value. This hypotenuse of the triangle, we use an r to label because it actually is the radius of a circle. So if you imagine our initial arm is here, if we were to rotate all the way around, we form a circle. And so this is actually the radius of the circle. X can be negative if it's over here. Y can be negative if it's down here. But because the radius is a distance measure, that will always be a positive number. We know from grade 10 that the sine ratio is opposite over hypotenuse. So I can define my opposite side by the y value of that number. And my hypotenuse of this triangle is that radius. So I can write my sine ratio here as the sine of that angle is the y divided by the r. Similar for the cosine ratio, we know cosine is adjacent, so this is the adjacent arm, divided by the hypotenuse. This is the hypotenuse. So we can take that x coordinate and put that number here, and we can put the radius here, and that forms our cosine ratio. We know tangent is opposite over adjacent. So from this angle, y is my opposite side, x is my adjacent side, and that gives me my third primary ratio. If we know the x-coordinate and the y-coordinate, we can calculate that r value by using Pythagoras' theorem. This is the simplified way of writing that a squared plus b squared equals c squared being your radius. I got rid of the squared by square rooting. All right, so take a look at the first example here, and I'm going to terminate in quadrant 1. My point on that terminal arm is 4, 2. That's how I know I'm in quadrant 1. Both x and y are positive. You can also just sketch it out and take a look at it. So just really roughly, I went 1, 2, 3, 4 on the x-axis, 1, 2 up on the y-axis, and I plotted that point. So I know I'm 4 units over and 2 units up if I create that right angle triangle, and I can calculate r by using Pythagoras' theorem right here. So I did that. Remember, we want to pull out any perfect squares, so I took out that 4 times 5, square root 4, which gives us 2. So the simplified radical is 2 times the square root of 5. Now again, you can go back up here and take a look at this. I know my sine ratio is y divided by r. So if this is my angle, my opposite side is 2, my hypotenuse is that 2 root 5. So the sine of theta is 2 divided by 2 root 5. And think back to radicals. Remember, we don't want to leave a simplified answer with a radical in the denominator. I rationalize that denominator. So remember, this is equal to 1. When I multiply by 1, I'm not changing the value of the question. Multiply the numerators to get this, multiply the denominators to get this, and these will cancel out, divide to 1. So this is our simplified answer. Cosine of that angle, remember, cosine is adjacent over hypotenuse. So that's my x over r. So I can fill in 4 is my x-coordinate, 2 root 5 is the radius. Again, I rationalized. This is going to simplify down to 2 times the square root of 5 divided by 5. And the tangent, our third and final ratio, is opposite divided by adjacent. 2 quarters reduces to 1/2, so that's my simplified ratio. All right, and then I continued on. So my next one here, I now have a point on the terminal arm of -3, 7. So -3, we're going to go over here, and 7, we're going to go up here. So now I'm going to terminate in quadrant 2. I go through the same process. I calculate that radius by using Pythagoras' theorem. And again, the sine of this angle, now my angle of rotation is from here to here. So this is where I terminated. But because my right triangle is like this, and actually let me just draw in. This is a right angle here that allows me to use those primary trig ratios. So when I do that, I actually want not the angle outside the triangle, I want the angle on the inside. So I just put down, this is my reference angle, is what we're going to call that one. So from this reference angle, this is the opposite 7. My hypotenuse is the radius, which we calculated to be that root 58. So again, 7 over root 58, rationalized to get rid of the radical in the denominator, and here is my simplified sine ratio. The cosine from my reference angle is adjacent over hypotenuse. My adjacent side is the -3, my hypotenuse is that radius. I did not show how to rationalize every single time, because if we know we're multiplying by root 58 over root 58, I know that's just going to leave me with a 58 in the denominator, and I'm going to have that -3 times root 58 up here. So we can actually skip writing this down every time. If you need to write it down, by all means, go for it. But as you practice these, you're going to get a little bit more efficient with them. And then my final one is that tangent. So from this angle tangent is opposite over adjacent. I do not want to leave a negative in the denominator, so I kept the numbers the same. I just moved that negative sign up to the numerator. My third example, and there's a reason we're doing all of these, you'll see why in a second here. My third one, my point on the terminal arm is -3, -2. So I'm going to go -3 on the x-axis, -2 on the y-axis, and I'm going to draw in that vertical line to create a right angle. I'm going to calculate the value of r by using Pythagoras' theorem, and then again, I'm going to set up my 3 primary trig ratios. When you do it this time, I did rationalize. I didn't write down that I'm multiplying by the square root of 13 over the square root of 13, but you can if you want to. One thing, just remember, we don't want to leave a negative over a negative. A negative divided by a negative is a positive, so that's where that value came from. And then in my final example here, I'm going to fill in, this is my right angle. We now terminate in quadrant 4. That's the Roman numeral for 4. So again, my point on the terminal arm is 4, 1. So I go over 4 on the x-axis, down 1 on the y-axis, and I calculate that radius value because now we've rotated all the way around to here. I'm going to set up my 3 primary ratios. I'm going to simplify, and we're going to get those as our simplified ratios. Now, here's what I want you to notice. When we terminate in quadrant 1, because x is positive and y is positive, and the radius will always be positive, notice that all of those ratios are positive. When we terminate in quadrant 2, that means x will always be negative, y will always be positive. And so what happens when we do that is we end up with a negative cosine ratio and a negative tangent ratio. The reason sine is positive is because my opposite value is positive and my radius is positive. I'm not using the adjacent side in the cosine ratio, so that's why sine is positive. When we terminate in quadrant 3, notice tangent is my only positive ratio. And it's positive because when I go the opposite divided by the adjacent, a negative divided by a negative becomes a positive. But in each of these cases, because my opposite side and my adjacent side are negative, we end up with a negative cosine or a negative sine and a negative cosine. When I terminate in quadrant 4, now x is positive, y is negative. So that means when I put my ratios in, the only positive ratio is that cosine one because my adjacent side is positive, my hypotenuse will always be positive. So the way that you can remember this, and we do need to remember this for what we're going to do, is we call it the cast rule. So in quadrant 4, this is quadrant 4 that we're terminating in. The only ratio that happens to be positive is cosine. So C stands for cosine. In quadrant 1, if we go back and take a look, all my ratios are positive when we terminate in quadrant 1. So in quadrant 1, I'm going to fill in all 3 primary trigonometric ratios are positive. When we terminate in quadrant 2, the only positive ratio is that sine. When I terminate in quadrant 3, the only positive ratio is tangent. So when I terminate in quadrant 2, sine is positive. When I terminate in quadrant 3, tangent is positive. So we call this the cast rule because if you can remember, C goes here. If we rotate counterclockwise, it spells cast. Some people like to go this way and say ax, but because angles in standard position always rotate counterclockwise, most people find it easier to think of this as the cast rule, which we're now going to use to do some calculations. I pulled my calculator up here, and we're going to take a look at what happens when we try to find the sine of an angle greater than 90 degrees. Similar to what we did for the 10C material, make sure you're in degree mode. If I type in the sine of 130 and we're looking for the ratio, I get that value. So I rounded it to 4 decimal places. This is the ratio, any triangle that has a 130-degree angle. If we divide the opposite side by the hypotenuse, this is the ratio that we will get. Now, if I do this one over here, the sine of 50, you're going to notice what happens is we end up getting the same ratio. So in this case, sine of 130, I know this is 0, this is 90, this is 180. So I know that 130 degrees is going to be between 90 and 180. So we're going to be approximately there. So if I rotate from here to here, that's 130 degrees. I have a 50-degree angle. 130 plus 50 gives me that 180 degree straight angle. I moved my calculator out of the way so that you can see the bottom of the screen here. We call that angle in green, this 50-degree angle, the reference angle. A reference angle is an acute angle, so it's between 0 and 90 degrees, between the terminal arm of my angle in standard position and the x-axis. So here's the x-axis, here's my terminal arm, there's my reference angle. On this one, here's my x-axis, here's my terminal arm, there's the reference angle. Here's the x-axis, here's the terminal arm, here's the reference angle. Likewise, this is an acute angle here. My reference angle is just the same as my angle in standard position. All right, going back to the cast rule. We know if we terminate in quadrant 2 that the only ratio that's positive is sine. My second example has cosine, so you can put this into your calculator and see you end up with a negative value. So the ratio, the adjacent side divided by the hypotenuse, is the same, but this is negative because any cosine ratio terminating in quadrant 2 is negative. Similar, this one, we have a 170-degree angle. We know that's between 90 and 180, so we terminate in this quadrant. So we know if we terminate in quadrant 2, sine is positive, every other ratio is going to be negative. However, the value of these, the absolute value of those, happen to be the same. Because again, if this is 10 degrees, my reference angle is also 10 degrees because 10 plus 170 gives me that 180 degree straight angle. 150 plus 30 gives me that 180 degree straight angle. Okay, so here's the last thing we're going to do today. We're going to say, can we find a missing angle given a ratio, one of the primary trigonometric ratios? Now remember from grade 10 or last week, in order to find this angle, we need to use that second function of the sine, take the inverse of that sine. In grade 10, we focus on finding the angle between 0 and 90 degrees. We're now going to expand and say, what are all possible angle measures between 0 and 360 degrees? So we're going to do a full circle on this one. We're going to go between 0 and 360 degrees. All right, so the first thing we need to do is get that angle measure. So I'm in degree mode. I'm going to go second function sine to take the inverse, and I'm going to enter that 0.5. So that's the opposite side divided by the hypotenuse. And when we do that, we get 30 degrees. So I know my angle is 30 degrees. Now, here's what this tells us. So in quadrant 1, we know we have a 30-degree angle. All trigonometric ratios are positive in quadrant 1. Because this is a sine ratio, we're going to take a look and say, where else in here is sine going to be positive? Because this is a positive value. Well, we can also see in quadrant 2, sine is positive. So now if we were to draw the second one in, so let's put in our second arm. If my reference angle is 30 degrees, we're going to say, what is my angle of rotation to go from here to here? Well, clearly, if we know this adds up to 180 between here and here, if this is 30 degrees, we can go 180 minus that reference angle, and we know our second angle is going to be that 150 degrees. All right, so I filled in here. So given the sine ratio of positive 1/2, these are the two angles that have that 1/2 ratio. You always want to draw this out to be able to identify in which quadrants is your ratio either positive or negative. So taking a look at the second one, I went ahead and filled this in here. We're going to first of all get that reference angle. So we're going to go second function cosine, 2 divided by 3 in our calculator, and we're going to get that 48 degrees. We're going to go over to our diagram and say, okay, this is a positive ratio. In which quadrants is cosine positive? Well, we know all ratios are positive in quadrant 1. Cosine ratios are also positive in quadrant 4. So if I'm in quadrant 1, my reference angle is just that angle of rotation. If I'm in quadrant 4, I'm going from 0, there's 90, 180, 270, and we're going to keep going. I know my reference angle is between the positive x-axis and my terminal arm. So that means 48 degrees is here. So how do we get that angle of rotation in purple? Well, we know one full rotation, a complete circle, is 360 degrees. So if we take 360 degrees, subtract that 48 degrees, that will leave us with our angle in standard position. All right, so carrying on here, let's move down to this one. So tangent, we know tangent is positive in quadrants 1 and quadrants 4. So when I draw this out, quadrant 1, that is just my 45-degree angle. Quadrant 4, now I'm rotating all the way around to here. I know my reference angle, and again, it's between the x-axis and the terminal arm. That's 45 degrees. So in this case, we know from here, there's 90, there's 180. We add another 45 degrees, and that gives us our second angle of rotation. Now, you're going to eventually get ratios that are not positive, that are negative. So now with this one, we're going to say, okay, they've already divided the fraction to get this value, but we have a negative. So now we're going to say, in which quadrants is sign negative? Well, if it's positive in 2 and 1, it's negative in 3 and 4. So our angle is going to terminate in those quadrants. So we can draw this out here. So my reference angle, one thing, when you put this in your calculator, ignore the negative sign when you put it in. Just go second function, sine 0.0856. Some calculators get finicky with the negatives. It doesn't really know how to handle them. So leave it off when you put it in your calculator. I'll write that down in a second. Get the reference angle. And then again, we're going to say, okay, so if I terminate here, that reference angle is 5 degrees. It's between the x-axis and my terminal arm. So I'm going to go around. There's 180 plus another 5 gives me 185. And then again, my reference angle is between the x-axis and the terminal arm. That's 5 degrees. So I basically go 90, 180, 270, and I don't quite go 360. I'm 5 short, so I remove that 5, and we get 355 degrees. All right, so we have a couple more examples here, and I'm not going to go through them in great detail. You can take a look at them on your own. But the important piece when you do these is to remember that you always want to draw a diagram. So you want to take a look and say, okay, quickly draw a sketch. I would, in the beginning especially, write out your cast. Say, do we have a positive or negative ratio? And then look to see which quadrants is that ratio positive or negative in. We know cosine is negative in these two quadrants. Then sketch your terminal arm. Use your calculator to get that angle of reference. Put that on here, and then it's a lot easier to see. Are we adding or subtracting that value to either 180, 360 to get those angles in standard position? And then from there, you know what you're doing. All right, have fun with this.